Hi everybody, and thank you for watching our first video on our course Laser Physics. And as the name suggests, we will be first introducing to you spontaneous emission, stimulated emission, and absorption as processes. And these of course form the kind of like a fundamental processes that help us to understand how lasers behave. So let's just get started by considering two energy levels that we just label with numbers 1 and 2. And these two energy levels would be describing a system of forming consisting of atoms or molecules. So essentially these different energy states, they are also associated with respective energies E1 and E2, and the notation goes in a way that the energy of E1 is smaller than the E2. So in our terminology, the level number one is also known as the ground level or ground state, and the level 2 is known as the excited state or excited level. And this picture hopefully clarifies the situation, how these levels are being formed with respect to the energies of each other. So here we have the first energy level, often denoted with a G as in the ground level, and here we have the higher energy level E2 or E using the bracket notation here. In case you're not familiar with this bracket notation, don't worry, it's just a notation describing that there's some kind of quantum mechanical state describing the electron wave function and thus also the state and the energy. And these arrows in our pictures, they describe usually a photon raising an electron here from this state into a higher state, and then possibly also de-leveling or relaxing an electron from an excited state into a lower state. So this is a kind of picture describing how things work out. The energy difference E2 minus E1 is released by the atom or a molecule, or in principle, of course, it could be a semiconductor system there too. In any case, a system of an active medium. And then when this happens, the system relaxes the energy, relaxes from the excited state into the ground state. And that's the process known as spontaneous emission. The frequency, nu naught of the radiated wave, is given by nu naught equals to E2 minus E1 divided by the h, so that would be the Planck's constant, and then the spontaneous emission of this photon corresponds to an energy of h times nu naught. If you prefer to use angular frequencies instead of frequencies, of course, we would be using the reduced Planck's constant, so h bar here, and then the angular frequency omega naught would be describing the energy. So this is a spontaneous emission process. That's one of the kind of fundamental processes that can take place when we are looking at the atomic system of emitters. So the energy of a photon is like this, and it causes the atom to decay from the excited state from the level 2 into a level 1. So this is in a nutshell what happens when we are considering a two-level system, and we are considering excitation and subsequently a spontaneous emission process. Now, radiative emission is one of the possible two decay mechanisms out there, how the system can decay or relax its energy. So the other one is called non-radiative decay, and I will next outline to you what is the difference between these two different mechanisms. So in a non-radiative decay, the energy difference E2 minus E1, or part of it, could be also like a small portion, and this is usually actually the case, is released in a form other than electromagnetic radiation. So what this means is that, for example, we may have a little bit of more kinetic energy in the system. This would be the case especially when we would be treating a gaseous medium as our gain medium, as our active medium, or it could be also stored into an internal energy stage of our system. And this would be more what happens in a semiconductor laser system or a solid state system or fiber lasers, of course. So part of the energy is being stored also into the surrounding atoms or molecules, or in a way is being released into the surroundings. In practice, what this really means, and this is really important in terms of understanding how lasers behave, how optical amplifiers behave, and what are the limitations. Well, what happens here is that now material heats up. So part of the energy we use or pump into the system also causes the material to heat up. And this is a big thing in terms of real practical devices. And here I'm just outlining with these two schematics the processes in case. So this would be the radiative emission, so spontaneous radiative emission. The energy totally relaxes, or the electron state totally relaxes into the ground state and releases a photon spontaneously corresponding to this energy difference. And this is the radiative transfer. And then here I'm trying to highlight what happens in this non-radiative decay. So instead of this state labeled with the number 3, now instead of like a relaxing directly from energy state 3 to energy state 1, we have a kind of intermediary state here labeled with the labeled with the 2, and then part of the energy is being transferred into the system, not in a form of a photon emitted, and then finally we will have a spontaneous emission taking place, radiative transition here from the energy state 2 into the ground state, and this will be the photon emitted out. So this is our part of energy that actually is being also stored into the system, and this would be basically that gives rise to material heating up. So it could be, for example, increase in the kinetic energy or increase in the internal energies. So for example, vibronic or vibrational energy states of a solid state. So phonons, atomic lattice vibrations that now would take place inside the material. Now, if you look things holistically from the kind of big perspective, fundamentally, of course, we do have 3 different fundamental light matter interactions in a 2-level system, and this of course generalizes to more complicated systems too. So 3-level or 4-level energy systems. So we may have absorption, light photon comes, interacts with the material and raises an electron from the ground state into the excited state. We may have stimulated emission that you have already heard about in high school physics. That is a kind of like the main process that we utilize to make lasers. And then we may have the spontaneous emission that we already described. And I'm showing these a few processes as schematics here. So this is the spontaneous emission. An electron state relaxes spontaneously, emitting a photon corresponding to the energy difference. The energy of the photon corresponds to the energy difference of the electron states. Then we may have absorption. So in a way, this is the reverse process. So we first start with an electron state at a lower energy state. Then an incoming photon of a given energy raises this electron into a higher electron state. And then we may have a stimulated emission process where this relaxation of an electron from the higher energy state into the lower energy state takes place via stimulated process. So a photon of right energy interacts with the material system, and subsequently electron is being relaxed into a lower energy state, and now we have 2 output photons emitted that actually are having coherence with respect to each other. So this would be the stimulated emission, and this is the main mechanism that gives rise to possibility of making lasers. Now, let's start by looking into these processes more in detail. So we consider first the spontaneous emission process, and now what happens, we are considering spontaneous emission. We are interested in the electron states in the higher energy state value. So the population of the excited states is of our interest. And now what happens in this process is that this population of excited states relaxes towards the ground state or into the ground state. So quantitatively, this can be described by defining A as the rate of spontaneous emission. So this is also known as the Einstein's A coefficient. And this parameter, basically, it's the fraction of population that actually decays to the ground state in an infinitesimal interval of time. So it's a rate of spontaneous emission. And the population of the following excited states evolve in time according to a following rate equation. So we are now really interested about the dynamics of our system. So the time derivative of the excited state population. So here, please see this N2, that's the population of the excited state. And then we are interested what happens with respect to spontaneous emission, and we are interested how this rate changes. And this is basically the differential equation that governs the dynamics. So we have minus A, that's the Einstein's A coefficient, times the population of the excited state. So very simple differential equation giving us the rate equation for a spontaneous emission process. So this is how difficult the differential equations basically look like in our course. Please note in the previous differential equation that we do have a minus sign. So of course this means that the population of the excited state decreases as a function of time. So that's why we do have the minus sign there. So physically what happens is that we have relaxation of the excited state into the ground state. I don't go into the details how do you solve that kind of differential equation. This is basically already done at high school when we are looking at radioactivity and radioactive decay of materials. The solution is an exponentially decaying function of this form. So essentially we have the population of the excited state N2 as a function of time, and that equals to the population at an time interval of 0 at the kind of like a origin of time, and then we have an exponential decaying function e to the exponent of minus t divided by tau sp. And here the tau sp is essentially a spontaneous emission lifetime or radiative lifetime. So that's defined as the inverse of the Einstein's A coefficient. So this is the math, and the actual value of tau sp is a property of the medium or the system, and that depends on the particular energy transition considered. So now what actually is this value, how it's being calculated. In principle, it's being calculated through the Einstein's A coefficient calculation. More on that later. And here it's important for you to know that medium, what kind of gain medium we have, what kind of atoms, what kind of molecules we have dictates, and what kind of transition we are looking at dictates how quickly or slowly the relaxation takes place. And those of you who are really interested also on the quantum properties of light, I just put this system there marking that in principle the lifetime is also being dictated by the surroundings. So if you put an atomic emitter inside a high quality factor resonator, then the resonator starts also affecting the radiative processes. So essentially we need to start taking into account the fact that light is not just a classical electrodynamic radiation, but rather it is a quantized field or quantized fields, and their quantization is being dictated by the environment. So essentially by the properties of the resonator. And then we are entering a regime that is not just entirely adequate to describe the light-matter interaction using a semi-classical approach as we do on this course. But we do not go into that kind of treatment in this course. In terms of understanding how lasers behave, is purely adequate to use a semi-classical treatment. So we only need to most of the time consider what's our medium giving rise to the properties of the spontaneous emission and also the stimulated emission. But I just wanted to point to you in case you're interested that that would be a kind of one approach where you can go beyond the semi-classical treatment, because sometimes people are really interested about this kind of quantum mechanical treatment and quantum mechanical properties of light. So when we are looking at light instead of classical field as a bunch of photons. Now, this is how the population evolves as a function of time. So it's a simple exponentially decaying function, and the radiative lifetime tau sp basically varies roughly from a few picoseconds to some milliseconds when we are looking at electrodynamic processes. So basically when matter interacts with light. Typical values for this radiative lifetime ranges from 10 to 100 nanoseconds, depending on the material system when we are not looking at a strongly forbidden transitions. So basically we are not looking at phosphorescent materials. The physical meaning for this tau SP parameter, the radiative lifetime parameter, is basically that's the time required for the population of the excited state to have almost completely relaxed to the ground state. So if you really want to quantify this statement, we look at the time t equals tau sp, we plug in the value into the governing equation, and we get this kind of equality. So the population of the excited state N2 at a time interval of tau equals tau sp. That's basically the original population at time 0 divided by E. So that's roughly 0.36 times the original N2 population. So basically, approximately, that means that 70% of the population of the excited state has decayed to the ground state after accumulation of radiative lifetime tau sp time. So that's the kind of physical quantitative meaning what this tau sp parameter means. Now let's get forward. Let's next consider stimulated emission as a process. So now we are wanting to stimulate an emission process, and we are interested in the relaxation of the population of the excited state again. And now what happens is that this relaxation process is being triggered by an external electromagnetic field. So that's the meaning or the kind of physics behind the word choice of stimulated emission. And then this triggered external electromagnetic field interacts with the medium, giving rise to an emission process. The population dynamics, and we are really interested in population dynamics in what follows in our course, because that gives us a tool to write equations to understand the laser dynamics and the lasing action. The population dynamics, the differential equation is basically the same as before. So we are looking at the time derivative of the excited state population N2. And now we are looking at the stimulated emission process. So that equals to minus W21 times N2, where this W21 is the rate of stimulated emission. So this looks pretty much the same kind of differential equation as before, but now the devil is in the details. So what is actually underneath this W21 parameter? No, okay, unlike in the previous case, where the characteristic coefficient only dependent on the properties of the medium, now this time, like I already warned you, this W21 depends both on the medium. So, in other words, the transition energy between the excited and the ground state and the other properties of the medium. And in addition, it depends on the intensity of the incident interacting electromagnetic field. So this is where we have the difference between a spontaneous process. And in fact, this means that more photons interact with the medium, so stronger our pumping is, the more photons are also emitted through this process of stimulated emission. So this is really quantified by writing this rate of stimulated emission W21 as a sigma 21 times F, where this sigma 21 is the stimulated emission cross-section measured in the units of inverse meter squared. So that's basically how the medium affects this parameter, and then F is the photon flux measured in the number of photons per unit area per unit time, so basically in the units of inverse seconds per inverse square meters. So this is how things now are being changed. So in fact, we also have a importance or relevance of the photon flux playing a role in the probability of this kind of process to take place. Now, finally, we can consider just normal absorption. And unlike the previous process described above, absorption actually affects the evolution of the population of the ground state. So N2 is our parameter of interest, and this is behaving similarly as the stimulated emission process. So it's being influenced by an external electromagnetic field. And in this case, the rate of absorption, and now I'm labeling this as a W12, not as W21 as in the previous case of a stimulated emission. We can write the governing rate equation as a N1, the time derivative of N1 and that equals minus W21 times N1. So this is basically looking similar to the stimulated emission, but now we just like inverse the labels and so forth. So, as in the case of concerning the rate of stimulated emission, W12 is actually proportional to the absorption cross-section of our medium, so sigma 21, and then also of the photon flux. So the functionality is exactly the same as in the case of a stimulated emission. And please note that when we are looking at the absorption and stimulated emission processes, because the mathematics look similar, they are we could say that they are basically inverse processes of each other. So this is how one way of looking at it. And this is really not a coincidence. They are, in a way, inverse processes. And then they are more of a kind of fundamental property of the atomic medium, and implying ultimately that when we are looking at the kind of quantitative strength, how probable it is that some absorption process takes place, and how probable it is that a stimulated emission process takes place, the cross-sections of these respective phenomena are actually identical. So in other words, we really have an equality that the sigma 1,2, that's the cross-section for absorption, equals sigma 2,1. So that's the cross-section for a stimulated emission. So we can just denote them as a single sigma parameter. So that's how these things take place. And then I don't go into the details this time how this kind of proof can be shown, but basically I'll just point out that this equality was first demonstrated or calculated by Einstein and will be the subject of the next chapter. And then in terms of the kind of like a simple sentence trying to say what happens here, this identity that we just outlined to you means that the probability for the active medium, an active medium now just means a gain medium, so it means a material that where we can like raise electrons into an excited state, and then we can also like relax these in a kind of controlled manner. So basically we can make a gain medium that can be plugged inside a laser and make lasers. So the probability for the active medium to absorb an incoming photon is really identical to the probability for the same medium to emit a photon through stimulated emission. So this is in words what the equality means, and this is really fundamental and important to understand how lasers behave. So this is what I wanted to say about the first chapter on our course on laser physics. I hope you enjoyed, and next we will be going into the next one considering the laser idea. Thank you for listening, and please stay tuned. Bye.